All right, guys, so what we're going to be talking about here is we're going to be talking about something that is a little bit different. We're still going to be talking about convergence. It's very important when we talk about series that we understand what convergence is. But we're going to be talking about a type of convergence that's a little bit different. If you remember, we've talked so far about p-series. We've talked about a couple other things, alternating series, how we can tell they're convergent, geometric series. You can tell how all of those are convergent and whether or not they're convergent. Now what we're going to do is we are going to look at something, again, that helps us out a little bit more in determining what convergence is. So when you think of all of the series that we've looked at, other than alternating series, here's a couple of observations that we may have looked at. Now again, alternating series works a little bit differently. But one thing that we were trying to look at is we were looking for convergence, and we were more or less just trying to determine how fast these different series were getting close to zero, or how fast their terms were getting close to zero, to find out whether or not that happened quickly enough so that we could tell that the series was convergent. And so that was one of the things we were looking at. Remember, when we're looking at like a p-series, we just wanted to see what the power was that it was raised to, or what the number was on the bottom. And once we saw that, we could tell very quickly whether or not it was going to be convergent. The other thing that's very important to realize when we're looking at a series that we've looked at so far is we were only looking at series, other than, again, alternating series that had positive values. On an alternating series, what we were looking at is values that went between positive and negative, positive, negative, positive, negative. And that happens an awful lot then when we have a series like that, where we can see for a fact that it is indeed an alternating series. What we have is we can use that alternating series test like we talked about before. What happens sometimes, though, and this is usually with series that involve some sort of sine or cosine, where one value to the next value will not always be guaranteed that we go positive, negative, positive, negative. So they're not alternating, but some values are positive and some values are negative, is we look for what is known as absolute convergence. Now you can see the definition of absolute convergence here. It says if the series from 1 to infinity of the absolute value of a sub k converges. In other words, if we look at the absolute value of every term in the series and that converges, then the series itself converges. Okay? Again, that's what is known as absolute convergence. And we won't use it a ton more here, although it leads us into what we're going to talk about next, which is what is known as the ratio test, which is a very, very important test that we're going to be talking about. And again, we'll get to that idea soon. But in order to show absolute convergence, so this is a question you'll be asked sometimes. You'll look at a function like this, you'll say, is this function absolutely convergent? The way that we figure that out is we more or less put absolute values around each individual term to find out if overall the series itself is convergent. Now, if you think about this, plugging numbers in, plugging in 1, plugging in 2, plugging in 3, what I get is I would get like 1/2, then I would get 1/4, then I would get 1/8, then I'd get 1/16, and I would just add all of those numbers up. Now you'll notice the only thing that the absolute value did is it made it so that each term doesn't go positive, negative, positive, negative. It just makes all of the terms be positive. Other than that, we find all of the terms exactly the same. Well, looking at this new series that I have that doesn't have the positives or negatives, I could say hopefully you recognize a pattern. The pattern here is that from the first term to the second term, from the second term to the third term, each time it's half as big as it was before. What we have here is a geometric series that the ratio is less than 1. So my ratio is less than 1. Since that ratio is less than 1, we know that this series is convergent, the one that we're looking at. Now, because we use the absolute value, instead of saying the series is just absolutely or just convergent, we say that it is absolutely convergent. And the absolutely just means I put absolute value around it, got rid of the fact that it's going negative, positive, negative, positive, and the series was convergent because of that. Okay? So hopefully that kind of makes sense on what it means to be absolutely convergent. Let's take a look at another one. Okay? I look at this and I can see that this is the alternating harmonic series. We learned last time when we were talking about alternating series that this series was indeed convergent. But if I put absolute values around it, what that does, again, is I get 1 plus 1/2 plus 1/3 plus 1/4. That is just the harmonic series, which we have learned is divergent. Since that series is divergent, then we would say that this is not absolutely convergent. That doesn't mean that the series itself is not convergent. Oh, and I wrote series instead of convergent. The series itself, we already know that it is convergent, but we would say that it is not absolutely convergent. Now, when something like that happens, we have a situation where we say that that particular series is conditionally convergent. When I say it's conditionally convergent, what that means is the series originally was convergent, but when I take away the alternating series portion of what's making that series be convergent, in other words, I get rid of the fact it goes positive, negative, all of a sudden the series is no longer convergent. So, and you can read it here, basically if the series is convergent both with and without the negative values, we say that the series is absolutely convergent. If it needs the negative values to make it more or less be like an alternating series or something like that in order to be convergent, then we say that the series is conditionally convergent. And again, it works a little bit differently. Now, when I say this, I'm saying if this series with absolute value converges, then overall it converges. When you see that statement, and you might see it on the AP test, where a certain series with absolute value around it, they're saying it converges, you can assume that this converges as well due to being absolutely convergent. In other words, it's more difficult to be absolutely convergent than it is to be just plain old convergent. It's like a higher level almost of convergence. And again, you might be saying, well, why do I really care about this? Why does absolute convergence really matter in the grand scheme of things? It allows us, again, if something is absolutely convergent, it allows us to use the rule that we're going to use in just a second, or rather in the next topic that we talk about. Okay? So this one right here, does the following converge or diverge? Well, I've got the sign of K right there. Now, the problem here is this right here would be going back and forth and back and forth and back and forth. Okay? But you'll notice that I have myself a P series here. That number, if I were to just put absolute values around this, that would make it so that I get just the biggest or the smallest the sign will ever be is 1 over K to the third. So if you think about it, I'd get like 1 plus 1/8 plus 1/27 plus on and on and on. Because that number is greater than 1, we have a P series that is convergent. Since that is convergent, that means that this series is absolutely convergent. Since it's absolutely convergent, that means the entire series must be convergent as well. So again, if you're absolutely convergent, your original series is going to be convergent as well. If you're not absolutely convergent, it's still possible your original series is convergent, but you don't know for a fact whether or not it's going to be. So again, that's a little bit confusing, but hopefully that makes sense. If you're absolutely convergent, then you know for a fact that the original function is going to be convergent. If it's not absolutely convergent, it's still possible that the original function is convergent, but we have to use a different test to try and find out what that is. So again, hopefully all that makes sense. If you have any questions at all about that, please let me know.